Good morning, students. Today we will start with the concept of magnetic field due to a current carrying straight conductor. So if you remember, in previous class we have learnt about Ampere's swimming rule. So what does that mean, Ampere's swimming rule? According to that rule, what was it? We were able to find out that in which direction the north pole of magnetic needle is going to deflect when the current is flowing through the conductor. Fine. So now in that series only we are heading forward, and the concept is magnetic field due to a current carrying straight conductor. Just imagine that this is a straight conductor in which the current is going to flow. Okay, so in which direction is going to be the magnetic field? The direction of the magnetic field we have to find out. Fine. So before that, let us study something more, the setup, how to prove it, in which direction the current is going, magnetic field is going to show the direction. So when a current is passed through a straight conductor, let this be again A, B, then a magnetic field is produced around it. Okay, when the current is flowing through the conductor, then some sort of magnetic field is created around it. And how can we trace that magnetic field? That magnetic field can be traced by means of iron fillings. Okay, the scrapes of the irons, or a small compass, magnetic compass. Okay, either with the help of iron fillings or with the help of a small magnetic compass, we can easily find out the direction of the magnetic field around the straight current carrying conductor. So what should we do for this setup? Let us take a thick straight conductor, thick in the sense that it has a cross sectional area. Okay, so this is made up of copper. Okay, and it is A and B, and we are going to connect it. How? We are going to connect it to a rheostat, okay, a key and an ammeter. Clear? How? Let us see. There is an ammeter, fine, and a rheostat. You know what is a rheostat? Okay, rheostat. And a key in it, and battery. Positive, negative terminal. Clear? So this is how we are going to make the setup, and we have to insert this conductor through the cardboard. This is a cardboard, and we have made a hole and inserted this conductor through the hole, and it is going the another way also. Now the current is flowing through the conductor. So the direction of the current would be like, because battery is here, so the current is flowing from B to A, like this. Okay. Now what we are going to do before we start the experiment, we are going to sprinkle some iron fillings here. We are going to sprinkle the iron fillings, and as soon as we connect it to the battery, what is going to happen? The current will flow and magnetic field will develop, and we are going to slightly tap the cardboard. So what we will observe, that these iron fillings, they arrange themselves in the concentric rings. What do you mean by concentric rings? The rings which have same center or different radius. circle are drawn from the same point, same radius, same center, but of different radius. Fine. So such type of rings are said to be concentric rings. Clear? Now, how to find out the direction that the current is flowing through it and the direction of the magnetic field? So with the help of a compass needle we can find out the magnetic field direction. Okay. So the north pole of the compass is going to point in the direction of the field at any point. Okay. And the direction of these field lines is anti-clockwise. Okay. Now there is, if we are going to reverse back the current, like if it becomes, the battery is connected in such a way that this becomes positive and this one becomes negative. Now the current of flow will also change. It will become like this. So in this case, the magnetic field which is developed around the straight current carrying conductor is going to change, reverse. So what will be? It will become clockwise. Okay. So every time it's not necessary that we are going to have a magnetic compass to find it out. So what happens? We can detect the direction of the magnetic field by right hand thumb rule. What is it? By right hand thumb rule. Now what does this rule says? Just imagine this is the current carrying conductor. When the current is flowing from, say this is A, this is B, B to A, the direction is upwards. At that time what is going to happen? We will point our thumb in the direction of the current, the direction in which the current is flowing, say B to A, so upwards, so thumb is upwards, and the fingers which are going to curl, we are not to curl it actually, but imagine the fingers which are curling, like from which direction? From outwards to inwards. Okay. So these fingers which are curling, they will show the direction of the magnetic field. Again I am repeating. If the current is flowing from bottom to top, then the direction of the current is given by the thumb. Okay. Now this thumb is going to show, right hand thumb is going to show the direction of the current. Now what will be the direction of the magnetic field? It will be shown by the fingers which are curling around this current carrying conductor. Clear? Now let us take another case. The current is now flowing from A to B, means top to bottom. In this case, the current direction of the current flow is from top to bottom. So how to point out thumb? Thumb will be pointed out like this, because right hand thumb, we are going to point it down. Okay, because the direction of the current is down. Now what do you think is the fingers, how they are going to curl? They are going to curl, their direction would be from inside to outside. Okay, so same is happening here. When the current is flowing from B to A, so the current direction was like this. So how to point it out? In that case, it would have been anti-clockwise in previous case. Okay, but in this case, when the current is flowing down, so at this point what we are going to take? It will be from in to outwards, so we can say it is clockwise. Okay, the direction of the current is clockwise. Okay, so this is how we can find out the magnetic field due to a current carrying straight conductor. Clear? Now the things are quite important. What is a right hand thumb rule? So what does it say? The right hand thumb rule says to find, it is used to find out the direction of the magnetic field due to a straight current carrying conductor. This rule is being used. Clear? Now what is the rule? According to it, imagine that the straight current carrying conductor in your right hand, such that the thumb points towards the, is pointing in the direction of the current, and the direction of the curling of fingers will tell you about the direction of the magnetic field. Clear? So this was about the magnetic field due to a current carrying straight conductor. Fine. Now what is the magnitude of magnetic field here? What is the magnitude of magnetic field here? Let us see. See, the magnitude of magnetic field, magnitude of magnetic field is denoted by B. Okay, B, capital B. Okay, and because it is in some particular direction, so it is a vector quantity. Okay, and if the current in the conductor, say AB, is increased, then how the magnetic field is going to show the effect? The deflection of the needle of magnetic compass is going to also increase. If the current will increase, the magnetic field is going to increase. Okay, this is the reason that the magnetic compass is also going to show a lot of deflection. Clear? Now since the deflection of the compass is a measure of magnetic field, okay, so we can say that B is, or magnetic field is, directly proportional to current flowing through the conductor. Okay, this is the first equation. Now let us come to the second concept. Now second thing is distance. Okay, if we increase the distance between the conductor, current carrying conductor, and the magnetic compass, what do you think is going to happen? Just see, this is the magnetic straight current carrying conductor, and over here, and the current is flowing from A to B. Now here the magnetic compass is kept. So what do you think? How the deflection would be seen? It is going to show very less deflection. But if it is kept here, magnetic compass, what do you think? It is going to show lot of deflections. Yeah, it will be unstable. Why it could happen? Because of the distance, it matters. More is the distance between the magnetic compass and the straight current carrying conductor, then less would be the deflection. And if less is the distance, then more would be the deflection. So it means that if the distance of the compass from the conductor is increased, distance is increased, then what will happen? Then the deflection of the compass decreases. So it is inversely proportional. Okay, so we can say B is inversely proportional to R. Fine. So it becomes second equation, and if we combine both of these equations from equation 1 and 2, from equation 1 and 2, we get B is directly proportional to current upon distance. Okay, so this is the third equation that we have derived. Clear? Now, what is unit of magnetic field? The unit of magnetic field is Tesla. Tesla. Okay, and it was named after a Yugoslavian born American engineer called Nicholas Tesla. After his name, this SI unit of magnetic field is Tesla. It was named after Nikola Tesla. Fine. So it is in SI system. Fine. So learn till here, and if any queries you can discuss.